Hi everyone, today we are talking about lesson 7.1 and we're going to talk about modeling a data set and what a power function is and how this relates back to our logarithms. So you'll see on page 91 today that we have this observed braking distances that we're going to need for certain speeds. So if you're going 20 miles per hour, you're going to need a 20-foot braking distance all the way up to 65, where you need 220.5 feet of braking distance to come to a stop. So what we want to do with this is we want to create a linear regression eventually in our calculator. Now to do that, a couple of things. We want to make sure we have our correlation coefficient turned on. So if you look on that handout that I provided for you, to make sure that this happens, you really only need to do this once and it should stay on, but you're going to hit second 0, you're in your catalog, and then you're going to scroll down to diagnostics. Now to speed up this process, you're going to hit alpha x to the negative first, because that should bring you to the option D in the calculator. So to scroll a little bit quicker, since there's a lot of stuff that your calculators can do. And again, you want to scroll to diagnostics on, hit enter, and then enter again, and it'll be turned on. That should be the only time you have to do it, unless the calculator dies for some reason. Now from here, what we want to do is we're going to go back under the stat menu and we want to hit edit. We're going to type in that data that we see on page 91. So again, the stat menu will help you type that in, and the data is coming here to type in. Now, if for some reason you have data in one of your lists, like let's say here you have 1, 2, 3, and you want to clear out your list quickly, you could scroll up here to L3, hit clear, enter, and that'll clear that entire column for you. So I have this pre-typed in to go a little bit faster for us today. The next thing we want to do is make sure we turn our stat plot on. So if we do second y equals, we are going to see our stat plots menu, and then we're going to hit enter. And you should, hopefully it's defaulted to each of these things, but if it's not, you want to make sure that you get it defaulted there. And then again, you can kind of change up your markers and then make sure you hit enter so that it is on. And then we can quit out of there. And then last but not least, if we go to our window here, notice on page 92, when we graph this, we have a certain scale set here. So our x's are going up by 5s from 0 to 75, up by 5s. Then we're going from 0 to 280, going up by 20s on the y-axis. So we can kind of match up our graph. And finally, if we hit graph, then we should have our stat plot on, so we can kind of see that shape there. Now, whether you choose to graph it on here or not, if we see this picture, then notice it doesn't have a full-on linear feel to it, even just from the picture, but it's not the worst representation of a linear function. Now, to show the linear function itself, then what we're going to do is we're going to go again back to that stat menu. And again, these instructions are on that handout I gave you. But if we go under the stat menu and we scroll over to calculate, we want to scroll down to option 4, and we're going to take a linear regression of this data. And again, make sure it's your first list. We will hit calculate. And notice here we get our linear equation with y equals 4.412x minus 90.039. Okay, so nice quick way for us to get that data written down. So if we write this here, we see that this linear equation, a times x minus b here, plus 90, really. And if we tried to interpret this here, what we're really saying each time is that our slope, our m, right, and part of this, the slope, indicates braking distance increases about 4.4 feet. For each 1 mile per hour. And we also then see that the y-intercept doesn't really make a whole lot of sense in context, because if you're going 0 miles per hour, you don't need negative 90.039. So really our y-intercept then does not have contextual meaning. It's not because of it being negative. But mathematically, that's what it came up with, okay? Now, notice over here, there's this math tip box that I've begun to write over, and it talks about our correlation coefficient. The reason we had to turn our diagnostics on was so that we would see this correlation coefficient. Without your diagnostics on, that wouldn't pop up. And notice our R value is right around 0.977. And this isn't the world's worst correlation coefficient. It's pretty much indicating a strong positive relationship. So correlation on that. So it's kind of an increasing line there. And if we graphed it, this particular line, it wouldn't be the world's worst graph. This minus 10.09. It's not the worst graph ever, but to answer part D, like, it's still not perfect, and it doesn't definitely make sense on the situation. So it really isn't the best that we can do on this. And this is where today's lesson really comes in. And again, not quite on the line. So where do logarithms and everything come in? Why does this fit in? If we transform these so that we take the log of each of these values and the log of each of these values, I saved you some time, and you will see here this lovely chart of data. And what you want to do is you want to clear out those lists that you have. So again, we talked about if you go up here and you edit your list, if you need to clear out the data, scroll up and hit clear. It should delete everything out. And what I want you to do is to repeat this process that we just had. And it is a shortcut in order to fit this, or again, to fit, you have the scale down here. Another option I want to bring to your attention is the zoom stat option, zoom 9, because that will also help fit your data if you didn't want to look at the scale here. Okay, take a moment to do that, plot this data. Now, what you should see when you look at your graph is that it looks to be a little bit more linear. They appear to lie on or very close to this line here. And what you hopefully also noticed from all of this is if you perform another linear regression, this one's going to be a little bit stronger correlation coefficient. So take a moment to write the equation and look at the correlation coefficient. So this time we should have had an equation like so. And again, the correlation coefficient is about 0.997, which is very close to 1, aka a perfect fit. So it's really close to being a really good estimator for this data. And mostly because it's just even closer to 1 than our last correlation coefficient was. So that's what's important. Now, why do we need this? Where does this go from here? Well, if we were to take this data, and instead of calling this x and y in the equation, what we can do is we are going to take that y equals 2.071x, and we're going to substitute in everywhere we see an x and a y, we're going to substitute in log y for the y, and we're going to substitute in log x for the x. Because again, this log-log transformation, we're going to see can be rewritten in a way we really, really like here. Okay. Now, if we start playing around with this, if we move all the logs to, or if we look at our exponent first, we can take this coefficient out front and write it as an exponent. So we have log y equals log of x, 2.071 And then we want to move all of the logs to one side. So we have log y minus log x, so 2.071. Still have that negative on the right-hand side. And if we rewrite this, skipping a step, we condense this into one singular logarithm. We have log of y divided by x to the 2.071 still equals this negative. And now we can raise both sides, take a base of 10, so that this cancels. And this 10 to the negative 0.41, if we transform that, right around this 0.036. And on this side, then, we can multiply both sides by this x from the denominator, and we end up with that on the right-hand side so that it's no longer in the denominator. What this then is an example of, after all that transforming around, is a power function, which is the form a times x to the b. Remember, an exponential is a times b to the x, so we're essentially flipping these spots. Again, a and b are non-zero numbers here. So we can see that this is in fact a power function, right? This example here would be considered a power function because the a value is our, or the 0.036 would be our a value, and our b value would be the 2.071. So we have that formatting of a power function from that last problem. Now from here, what we are going to see is that our calculator could also use this function. So we're going to go back to the original data. I know you're not going to be very pleased with me, hence why I didn't delete it out. I'm not going to lie to you. But if we take this original data and again type that all in, and you scroll over to the calculate menu, then you're going to scroll down and you are going to look at a power regression. So that's down here. We're starting at letter A. And you hit enter, and the same thing applies when you're talking about calculate. And what you're going to notice, oops. Oh shoot. One more time. The power regression, we see that form of a times x to the b and our coefficient slash exponent. Notice that lovely r value that's much closer. So our power regression basically lets us quickly move into this. So again, it's the same, matching using that graphing calculator to find the power regression. Okay, so we could skip that middleman step of typing all that log transformed data in. Now we can then use this data to start predicting how much we would need, how much stopping distance we would need. In this case, if we plugged 70 in for x, we would get that we would need approximately 238.5 feet of stopping distance. So reminder, the faster you go in a car, make sure that you keep your stopping distance. And then one thing when it was talking about rounding our answer, the reason I chose to round to one decimal place right here is because the other data was rounded to one decimal place, but usually the more decimal places, the better. So that's why I just stopped there, though, because the other answers were. Last 2 points I wanted to bring up then. If you look at the bottom of page 95 with the check your understanding function, again, a reminder, when we talk about power functions are y equals a times x to the b, whereas our exponential functions are y equals a times b to the x. So they are not the same. Just something to keep in mind. because of that placement of our X and our B. And then last but not least, if our correlation coefficient comes out to be 0.542, then we know that this is indicating a weak relationship, right? A weak correlation because it is not close to 1. Or -1 for that matter. But the closer you are to 1 or -1, the more powerful your either positive or negative, if you're close to -1, correlation will be. Thanks, everyone.